Last video ended with a promise. Once you trust your sample mean and its standard error, you can put them to work. This is that video. By the end, you'll be able to explain the 6-step process of hypothesis testing, along with type 1 and type 2 errors and the power of a test, and construct a real hypothesis test given a level of significance. Hypothesis testing lets you use a sample to make a decision about an entire population with a known chance of being wrong. Every step exists to make that chance explicit, not to hide it. Every test starts with 2 competing statements. The null hypothesis, written H0, is the claim you're trying to reject. The alternative hypothesis, HA, is what you accept if the evidence is strong enough. Together they have to cover every possible value. Nothing can fall outside both of them. One rule makes this easier than it sounds. The null hypothesis always contains the equality. Whatever you suspect or hope to find, a fund beating its benchmark, a difference between 2 means, usually belongs in the alternative, not the null. Watch the wording because it decides the shape of the test. If the claim is that a mean is simply different from some value, that's two-tailed. The alternative points in both directions. If the claim is that a mean is greater than or less than some value, that's one-tailed. The alternative points one way, and the whole rejection region sits in a single tail. Try it. A fund's return is expected to differ from its benchmark. Yeah, that's two-tailed. A fund's return is expected to exceed its benchmark. That's one-tailed, and the alternative points only up. Get the wording right, and the rest of the test follows automatically. There are 6 steps, and they're the same every time. State the hypotheses. Identify the test statistic and its distribution. Specify the level of significance. State the decision rule. Calculate the test statistic. Make a decision. Let's run all 6 on a real example. Nexora Growth Fund has returned an average of 1.8% a month over the past 30 months, with a standard deviation of 4.2%. Its benchmark averages 1.2% a month. Is Nexora's performance genuinely different, or is this within the range you'd expect from chance? Step 1. State the hypotheses. The null is that the true mean equals 1.2%. The alternative is that it doesn't. A two-tailed test, because we're asking about a difference in either direction, not specifically higher or lower. Step 2. Identify the test statistic. The population standard deviation is unknown, so this is a t-statistic with 30-1, 29 degrees of freedom. If the population standard deviation were known, which is rare in practice, you'd use a z-statistic instead. Because you almost never know it, t is the workhorse. That -1 matters too. Estimating the sample mean itself uses up 1 degree of freedom, leaving 29 independent pieces of information to estimate the spread. Step 3. Specify the level of significance. We'll use 5%, split across both tails since this is a two-tailed test, 2.5% in each tail. Step 4. State the decision rule. At 5% significance and 29 degrees of freedom, the critical t-values are plus and minus 2.045. Reject the null if the calculated statistic falls outside that range. Step 5. Calculate the test statistic. Take the sample mean, subtract the hypothesized value, and divide by the standard error. 1.8 minus 1.2, divided by 4.2 divided by the square root of 30. That works out to 0.6 divided by 0.767, a t-statistic of about 0.78. Step 6. Make a decision. 0.78 falls well inside the range of plus and minus 2.045. We fail to reject the null. There isn't enough evidence to say Nexora's performance is genuinely different from its benchmark. You'd reach the same place using the confidence interval from the last video. Build the 95% interval around 1.8% and it comfortably contains 1.2%. The two approaches always agree. One-tailed tests work the same way, with one difference. Suppose instead you specifically believed Nexora would beat its benchmark, not just differ from it. The null becomes the mean is less than or equal to 1.2%, and the alternative is that it is greater. The whole 5% rejection region now sits in a single tail, so the critical value moves into about 1.70 instead of plus and minus 2.045. Notice what fail to reject does not mean. It doesn't prove the null is true, it just means this sample didn't give you enough evidence to throw it out. Think of it like a courtroom. The null hypothesis is innocent until proven guilty. Convict an innocent person, and that's a type 1 error. Let a guilty person walk free, and that's a type 2 error. Neither risk is free. You're always trading one against the other. The stakes aren't abstract, and they're not always the same size. In a medical screening test, the null is that the patient is healthy. A type 1 error sends a healthy patient for unnecessary treatment. A type 2 error sends a sick patient home. Which error costs more depends entirely on what you're testing, and that's exactly why the significance level is a choice, not a fixed rule. Every decision carries a risk of being wrong in one of two specific ways. Reject a null hypothesis that's actually true, and that's a type 1 error. Fail to reject a null hypothesis that's actually false, and that's a type 2 error. The probability of a type 1 error is exactly the significance level you chose, the Greek letter alpha. Set alpha at 5% and you've accepted a 5% chance of rejecting a true null before you've even looked at the data. That number has a mirror image. Subtract it from 100% and you get the confidence level. 5% significance is the same statement as 95% confidence, just phrased from the other direction. The probability of a type 2 error is called beta. Its complement, 1 minus beta, is the power of the test, the probability of correctly rejecting a null hypothesis that really is false. A more powerful test is one more likely to catch a real effect when it exists. There's a second way to reach the same decision, without ever looking up a critical value. The p-value is the smallest level of significance at which you'd still reject the null. If the p-value is smaller than your chosen significance level, reject. If it's larger, fail to reject. Same conclusion, different route. And it's the version most statistical software actually hands you. Suppose a different test produces a p-value of 3.2% against a 5% significance level. 3.2 is smaller than 5, so you'd reject the null there without ever looking up a critical value. Here's the trade-off worth memorizing. For a fixed sample size, lowering alpha to reduce type 1 errors automatically raises beta and increases your type 2 error risk. You reject less often overall, including when you should. The only way to bring both errors down at the same time is to increase your sample size. A bigger sample shrinks the standard error, the same standard error from the last video, which sharpens the whole test. Watch what that does to Nexora's own test. Quadruple the sample from 30 months to 120, and the standard error shrinks from about 0.77% to about 0.38%, roughly half, exactly as the square root rule from the last video predicts. The confidence interval tightens to well under 1% either side. A true effect and a false one both become easier to tell apart correctly. More data, not a lower alpha, is the real fix for a low-powered test. Your turn. A researcher sets a very strict 1% significance level instead of the usual 5%, keeping her sample size the same. Does this raise or lower the probability of a type 2 error? It raises it. A stricter significance level means a smaller type 1 error, but with the same sample size, that always comes at the cost of a higher type 2 error probability. Quick recap. 6 steps every time. Hypotheses, test statistic, significance level, decision rule, calculation, decision. The null always contains the equality, and it's the hypothesis you're trying to reject. Alpha is the probability of a type 1 error, rejecting a true null. Beta is the probability of a type 2 error, failing to reject a false one. Power is 1 minus beta. And the trade-off, lowering alpha raises beta for a fixed sample size. Only a larger sample brings both down together. Next time, 5 more hypothesis tests, variance, the difference between two means, paired samples, and when a parametric test isn't the right tool for the job at all.